So for a couple announcements here, really just one announcement. The Unit 16 assessment is the one that's due tonight. It is a little bit shorter. There's not as many questions, both in the work section for you to review or in the assessment for you to take. So if you started it, then you've already seen that. If not, just a heads up on that. Hopefully that's an advantage for you. The other thing I'll mention about that is there's, depending on which questions show up, you might see one part of a question, I think, that asks about work. So if you go through the video, it kind of helps talk about that a bit. If not, we're going to be actually talking about that today. So hopefully that'll help you if you're stuck on that little portion. And it depends. You might not see that in the ones that get chosen for you because there's only, I think there's only 4 sections of questions that you have questions from. And it's like 1, 1, 1, and 2 or something like that. So, or 1, 1, 1, and 3, I can't remember, but the most questions are on the vocab. And so it's just making sure you understand the terminology. For I think there's maybe 3 work questions and 3 vocab questions, if I remember right. And for the 3 work questions, it just depends on which ones you get, whether that will show up for you or not. So today's lesson may actually help you just a bit with that. But that's due tonight, and today we're actually starting the next unit, energy, work, and momentum. And we've already briefly introduced you to the idea of energy, and we've also introduced you to the idea of momentum. Today we're going to bring in the 3rd key term here in this last unit, and that's work. But before we do that, I want to go through a little quick kind of brain teaser exactly, but a demonstration, but virtually this time, digitally this time. To have you see if you can figure out another race, but a more complicated race. Oh boy. All right, so on this race, we'll move this over here in the middle. So on this race, we've got a spherical shell, the green one.
Wait, Mr. Someone on the Zoom has to go to the bathroom. Like, would you press screen share like right once they say it? So, like,
Oh yeah, that's fine. Rocky, that's fine. If we look at this scenario, we've got a spherical shell, and they're giving you the equation for the I value of a spherical shell. So it's a hollow sphere, basically. Then they've got a solid sphere, and then they've got a cylindrical shell, and then they've got a solid disc or a cylinder. And then over here on the left, they've got this frictionless surface. You need friction for the other objects to rotate. It would be very minimal, but there has to be some friction, otherwise they just slide down the ramp. So to get them to roll down the ramp, there has to be a bit of friction under those circular objects. But for the frictionless cube, it's frictionless material for the cube and frictionless material for the table. And if we have this race of 5 objects down the same slope, starting from the same height, and they all have the same mass. So I think there's more information about that up here at the top, but I've got it zoomed in so you can see a little bit clearer. If they all have the same mass and they're starting from the same height on the same slope, which one wins the race? So in the Zoom, just type in the chat, which of these 5 do you think will win the race? The spherical shell, solid sphere, cylindrical shell, the disc, or the cube? And then for you guys here, think about it. You're ready to share your answers in a minute. We'll take a quick vote and see what we come up with. As soon as you have a guess, go ahead and type it into the chat. You have to guess.
they're thinking.
Yeah, it's okay to think. Okay, so we got to vote for solid sphere, solid cylinder.
This is the key.
Another solid sphere vote.
Yeah.
Outside the box.
Nice.
All right, so
Inside the box.
Inside the box.
just Johnny, what do you think? What do you vote for?
I vote solid sphere.
Solid sphere as well. So that one's getting quite a bit of votes. Andy,
I'm gonna go with the cube.
cube, Evan,
The cube just sliding, right?
Yeah, it's just,
yeah,
it's like it's some ice.
I'm gonna go with the cube.
gonna go with the cube.
Hey.
Kyle,
I'm gonna go with cube.
cube as well. Ethan,
Cube.
cube, Cade.
Cube.
Probably cube. Okay, wow.
Johnny,
So-
wanna change votes?
I'm good.
We started to have a lot of solid sphere votes initially, but a lot of cube votes towards the end. So let's talk about what we're seeing here, and then we'll check and we'll we'll compare the results to what we guessed. So you can see that the 4 rotating objects give you a rotational inertia value, and the one that cylindrical shell is just mr squared times 1. The fraction in front is just 1, so it's getting 100% of the inertia. And then if we go to the spherical shell, it's getting 2/3 or about 67% of the inertia. And then if we go to the solid cylinder, it's getting a half or about 50% of the inertia. And then the solid sphere is 2/5, about 40% of the inertia. Okay, so if we think about that, 100%, 67%, 50%, 40%, they all have different amounts of rotational inertia. So a lot of people picked solid sphere early on. It does have only 40% of the inertia. Remember, inertia is resistance to acceleration, so it has the least resistance to acceleration of the rotating objects. However, the frictionless cube is not rotating. So quite a few of you there at the end started
Cube's on a
picking
different
cube.
plane.
So why cube? For those of you that picked that, I don't think everyone that picked cube was in the classroom. So Ethan?
Well, the cube, it doesn't rotate, so it doesn't have to overcome the inertia. So it kind of just has an inertia. It'd be the same as if it had an inertia of 0.
Rotationally?
Yeah, so it can use all of the translational acceleration and not be hindered by having to speed up rotationally.
Okay, so are you saying it has no inertia or it just has no rotational inertia?
I'm saying it has no rotational inertia.
Okay, good.
Or it does have it, but it's not being accelerated, so it doesn't matter.
Right. Okay, gotcha. So it does have inertia, and if it could rotate, which in this case it wouldn't, it would have a rotational inertia, but it's not rotating, so it's going to be 0. But it still would have some inertia because even if it's just moving translation, it has its translational inertial mass. So, but you're saying that because it's not rotating, it's going to be accelerating all in the translational instead of rotational and translational?
Yeah, so last time we saw that a smaller inertia with the hoop and the cylinder made it go faster. And so if it has no rotational acceleration, then it doesn't have to use any of its energy on that inertia.
Okay, all right, well, let's check it out, see if we're on the right track, and then I want to come back to that.
There's a horse race.
All bets are in.
Oh,
Let's go. Let's go. Let's go. Yes.
So you can see the cube wins the race.
Let's go.
If we look at the other ones, we can see the disc is trailing behind. It has the most inertia, so it's the hardest one to accelerate. And then we'll let the race go just a little bit longer so we can see how the other ones are going to finish out here. The solid sphere has only 40% of the inertia, so it's going to be the fastest. It's going to have the least resistance to accelerate for those that are rotating. And then the disc is 50%, so it's a little bit more. And then the sphere is 67%, so it's a little bit more. And then the cylinder is 100% of the inertia that it has to overcome. So in terms of the rotating devices, the solid sphere wins in that realm, but the frictionless cube isn't rotating, it's just sliding. It's interesting because in first period, quite a few people picked the cube, but they all said because the rotating objects have frictionless and the cube doesn't, which is, I think, a factor. But the bigger factor is the energy connection. And Ethan started with more of an inertial focus in his explanation, which is great. But at the very end, he said a phrase, uses less of its energy or something like that. I don't remember the exact words, but he talked about energy. So that's where I want to focus today, because today's lesson is going to be about energy and work. So I want to direct our attention at that. At the beginning, what kind of energy do all 5 objects have?
Potential.
potential. And what it's gravitational potential, right? They all start at the same height and they all are experiencing the same gravitational acceleration, and they all have the same mass. So they all have the same gravitational potential energy. And as they race down the slope, that gravitational potential is becoming kinetic energy of motion. Well, how many kinds of kinetic energy are there? Two.
Rotational and translational.
Yeah, translational and rotational. Which one is going to determine the winner of this race? Translational. It's a translational race, right? So the one with the most translational energy will win the race. Now, all of the ones that rotate have both. Their initial potential gravitational has to split into both rotational and translational kinetic energy. Those two together add up to the initial potential it started with. But they have to divide that initial potential two ways, into both their rotational movement and their translational. The cube is not rotating, so it only has going straight from potential to translational kinetic energy. So all its gravitational potential becomes translational. So even if you ignore the fact that there is a little bit of friction that enables those round objects to, or circular objects to rotate, and there's no friction with the cube, it's really more about the energy. And you could see based on the math that they put into this simulation, it wasn't really a close race, right? The cube won pretty hands down. Whereas all the rotating objects are pretty closely clumped together, especially the three that have a lot of the mass more centrally located, right? All right, so just wanted you to think through, not only like we did before with inertia, but also with our newer concept of energy. All right, so the next thing I want to do is go to a problem on torque. So we're gonna have you practice a problem on torque. If you're at home, this is on worksheet 2, so you have a couple options. You could go to unit 7 and open up worksheet 2. You can see up here at the top it says worksheet 2 question 1. So if you want to do that, you can. If you just want to look at it on the screen, that's fine. If you are in class, same thing. If you can either get a copy of worksheet 2. I moved all the rotational worksheets to the back table now because we're kind of past that unit, even though we're going to keep reviewing. So if you didn't pick that worksheet up last week, they're still back there. If you did pick it up last week, then it's just find the one that's called worksheet 2, and it's the first question. And you can just obviously work this out without the worksheet, but if you'd like to work it out on the worksheet so you can see the question and the work on the same place, then whether you're on Zoom or whether you're in the class, you may want to have that open. All right, so let's read through this together. Then I'm going to actually have you try to solve it individually. So for in the room, I just want you to try to work on your own, see if you can figure it out. In the Zoom, I won't put you in breakouts. Just want to see if you can figure it out on your own. But let's read it through to make sure you understand the wording, what they're saying here. So it says we got a rod lying on the top of a table. So it's a lot like what we had on the previous question that we finished up with on Monday or Friday or Thursday, whatever day it was we met last. One end of the rod is pinned to the table so that the rod can rotate freely on the surface of the tabletop. Two forces, both parallel to the tabletop, act on the rod at the same place. So I'm going to pause real quick and come back, but this is the question we looked at last time. We had this meter stick rod pinned to the table, and we had two forces. Okay. The difference here is that these two forces were at different positions. It's still a top-down view. It's still forces parallel to the table, same scenario. The difference is, if we look at today's question, it says they act on the rod at the same place. Okay, so if I'm looking down from above, I don't know if you guys will be able to see this on camera or not, but if I'm looking down from above, one end is pinned, right, so that it's rotating. And now I've got two forces, but they're pushing at the same place. They're not at two different positions. They're at the same position. All right, that's what they're saying. And it says one force is directed perpendicular to the rod. And has a magnitude of 38 newtons. So it's perpendicular to the rod, but parallel to the table. The second force has a magnitude of 55 newtons directed at an angle theta with respect to the rod. So also an angle now, but an angle with respect to the rod, but still parallel to the table. If the rod doesn't rotate, what must the angle be in degrees? So take a few minutes, see if you can solve that one. I would encourage you to draw a picture. And I'll get the attendance in while you guys are trying that out.
Want radians? You sure you don't want radians? The calculator wants
It
radians.
really wants radians. For those of you in the Zoom, when you get an answer, go ahead and put it in the chat so we can see what you're coming up with. For those of you in the class, how many have an answer so far? Just one, okay, oh, two, okay, keep working for a few more minutes, couple more minutes. Ronnie, have you been able to come up with an answer, or are you still working?
No, I'm just trying to figure out, one little piece here.
Okay. Andy, how about you?
I'm a little stuck.
Yeah.
Okay. All right. Evan, you got an answer yet, or still working?
Well, I have a calculator, so I can get the answer.
Okay, you can borrow, I have 9 or so
I have
back
the
I
there.
could
potential to
calculate
have
it
an
if you want me
answer.
to.
Good have.
Yeah, well, go ahead and get a calculator so we can have one.
Do you want me to? do
Kyle, you
this
said
real
you have an
quick?
answer, right? So what did you get?
I got 43.7 degrees.
Okay, Ethan,
That's the same as.
you get the same, Kate?
Yeah.
Okay. Sally, did you get an answer? Have you been able to figure it out?
Yeah, I got 40.93 degrees.
Okay, Rocky, how about you? Did you have a chance to figure it out? Not yet? How about you, Nat?
I'm a little confused.
Okay. Aiden, were you able to come up with anything?
Yeah, I got 43.7 as well, because I did like,
Okay.
Yeah.
Kyle, would you mind showing on the screen how you did your work?
Yeah.
Well, and just kind of talk it through as you do it, and hopefully they'll be able to hear you well on the microphone, and if they're a little stuck, they can kind of understand your logic.
Since it said that the forces equal out so that the rod isn't moving, that means that both forces can equal out to each other. So we know that one side is 38.0 newtons, and since it's perpendicular to the rod, that's times sine of 90, which we know is 1. And then the other side, we know is 55.0 newtons times sine of theta. And then, that's 1. So we got just 38, and then you divide 55 from both sides. So you get 38 newtons over 55 newtons equals sine of theta. Then you use you have to get the inverse sine of 38 over 55. So theta equals inverse sine 38 over 55. And so theta equals 43.7.
Real quick question before you sit down. Nicely done, well explained. I have one question though. Torque is FR sine of theta, so why don't you have an R there anywhere?
Because they didn't give us the radius. It didn't say like it was a meter stick or anything. It just said, or the placement of, or did it say?
No.
It
Yeah.
said it's pinned to the table.
Yeah, it didn't, but it didn't say the placement of the forces on the rod.
How can we ignore it?
Because we
Evan?
are,
Oh, you got it, Kyle?
or whoever can
Yeah,
go.
sure. Okay, Evan?
Because they're acting on the rod at the same place.
Yeah, so
Doesn't matter.
in that second line, it says acting on the rod at the same place. So we could put like R on the left and R on the right, but no matter what the value is, they're equal, so they would just cancel. Yeah. So while the equation is FR sine theta, the R is equal on both sides, so cancel. The one thing I would say in terms of just thinking College Board grader here, if you don't write an equation first so they can see what you're using, you wouldn't earn full credit. So
Okay,
you do want to make sure you write that FR sine theta somewhere at the top and then do the substitution.
gotcha. Okay.
Yep, good.
I have a question.
Yeah,
Technically, would there be 2 angles that it could be or no?
well, it tells you the angle. Oh, no, sorry. I see what you're saying. I thought you were talking about the perpendicular one. Yeah, so for this 43.7, it is 43.7 in terms of one way. Now, you could measure it the other way, but no matter which way you draw it, there's going to be a 43.7 degree angle between it and the rod.
Okay, so you don't have to get that.
Right,
Okay.
right. So if I understand what you're asking, Evan, and and just to make sure everybody else is tracking here with that question. If if this is the rod and I've got one force here, we could say, well, it's coming that way at an angle, or it's coming that way at an angle. We don't really know which one it is, but what we're finding is this. That's the angle we're looking at. So it might be pushing in towards the pivot point at that angle, or it might be pushing away from the pivot point at that angle. We don't really know that, and we can't say. But the angle it makes between the force and the rod itself would have to be that 43.7. Is that what you're asking?
Would you be incorrect if you gave both angles? Like, or if you gave both of them from one side, like, because I got 136 as well. Degrees.
Oh, I see. So you just measure it the other way. Let's see. Since it says with respect to the rod, I think they're wanting you to give the acute angle between the rod and the push, the force. Yeah. Mathematically, it's not incorrect, but just based on the phrasing, I think that's probably what they would want you to get. Now, if you drew it well and showed it well, then they probably would give you full credit, but you'd have to make sure it's a clear picture and that they understood exactly what angle you're measuring. But based on the phrasing of with respect to the rod, I mean, both of them technically are, but generally they mean the angle right between the rod and the force applied. So, any other questions on that one? I would always recommend drawing a picture. It just gives the grader more clarity on what you're doing, and definitely show an equation. So you could maybe have something like, you know, torque 1 equals torque 2, and then F1 R1 sine theta 1 equals F2 R1 sine theta 2. Because they both have the same R. You wouldn't even need to put the ones on there. You could just say R, right? But since it's at the same place, this phrase, we know that those R's cancel. So definitely make sure you show some kind of an equation so they can see your train of thought. And almost always in the rubric, it talks about, for those that you do have to do an actual calculation, it talks about showing a base equation, then showing the substitution. Now, all these steps here in the middle, you wouldn't have to show those. I mean, you may want to just so you can make sure you don't make any mistakes, but you wouldn't necessarily have to show these middle steps here, but you would need to show equation, substitution, answer. It's kind of the minimum requirement for almost all computation questions. We good on that one? Making sense? All right, if we have time at the end of the period, we may come back and do another one. For now, let's move on. So I'll clear this. And let's stop that share, go back to the notes. All right. So we've got the first two things. We did the ramp question. We did our first torque practice. We're going to define work energy and the work energy theorem today. And then if we have time, like I said, we may practice on another problem. If there's not enough time, we'll just give you that last bit of time to work on the positive physics assessment. All right, so let's start to define these terms. This is for chapter 7, and these next 3 weeks, we're going to be going over chapters 7, 8, and 9 in your textbook. So 7 and 8 are energy and conservation. You can see 7 is part 1 and 8 is part 2. Part 1's more foundational. What are the equations? What are the terms and definitions? And then part 8 is more the application. And then chapter 9 is on momentum. And so that's what we'll be wrapping up here is those 3 units. Last 3 chapters, 1 unit for us in these next 3 weeks. And then we'll be done covering material and just reviewing after the break. All right, so work. There's a lot of ways to define work. And unfortunately, some of the words we're going to talk about today are very difficult to define, especially energy. Work isn't quite as hard to define, so we're going to start with that. So one way to give a definition to the term work in the physics sense is it is an application of a force over a distance. So we are specifically defining work in a physics sense. And sometimes what we as humans would call work isn't really work in a physics sense. Another way to define it is the transfer of energy from one storage mode to another. So it could be from potential to kinetic, from kinetic to potential, could be from gravitational to kinetic to spring. Lots of different kinds of ways the energy could be transferred. But work is the transfer of energy from one storage mode to another. So a couple different ways to think about it. And that's going to lead to two different definitions mathematically, two different equations mathematically to solve for the amount of work numerically. Now, the second term, energy, is much trickier to explain because energy is not a physical tangent substance. Energy is an ability or a capacity. And so it's a bit harder to grasp and it's a bit harder to define in concrete terms because it isn't concrete. But one of the most common, very brief definitions you'll hear about energy is it's the ability to do work. So if you want to know what energy means with that definition, then you have to be able to know what work means, right? So we could rephrase that if we want. We could say, well, that means it's the ability to apply a force over a distance. Or just using the definition of work to expand on the meaning behind the term energy. Again, when we say it's the ability to do work, we're limiting ourselves to just work as defined by physics, not homework or that's a lot of work, but specifically in the physics sense. Yeah, Ethan?
So energy is the ability to transfer energy.
Well, you
Nice.
can't cover that, but we've got another one. We've got another way to phrase that because you don't want to use the word energy in its own definition. But here's another way to think about that. Energy is the ability to cause a change in structure or configuration or motion. Which is how the energy gets transferred from one storage mode to the next. So we avoid using itself in its own definition. Rethinking it a bit. So by structure or configuration, we mean maybe like its position, its shape. For a spring, is it compressed? Is it stretched? For an object, is it at a high height or a low height? We're thinking about its configuration in a system. And we're defining all of these things in systems. So not just as individual objects, but as a system. So for instance, if I say, hey, that box has a lot of potential energy because it's up on a high shelf. Well, it only has potential energy because of the Earth's gravitational force field. So the system is the Earth and the box. Okay, so we always have to think about things as systems, and that's going to be a big part of what we do on Thursday, is defining systems and making sure we have the correct things in the system. Not too much, not too little, but exactly what we need to have to define the work and the energy that we're referring to. The last term is a little bit easier to define again, and that is power. And power is a rate. It's the rate at which you can do work. So it's the rate at which you can apply a force over a distance, or the rate at which you can transfer energy, or the rate at which you can cause a change in structure figure. Like we can do all the substitution, take our math mentality. But another way to phrase it, and I would almost put the word consumed in quotations because it almost implies that they're saying it's used up or destroyed in some way. But it's, and often when we talk about like kilowatt hours and stuff, the amount of energy we use in our household, that's a power rating. But we're thinking about consuming it, but what we're really doing is just transferring it. So we take that electrical and we turn it into the mechanical of a drill, or we turn it into thermal energy to make our refrigerator work. So there's all different ways we transfer it. So it's consumed in the sense that it's transferred to a different storage mode, not consumed in the sense that it's used up. And we're gonna get to this in a little bit, but I want to go ahead and highlight it now. The unit for work is joules. The unit for energy is joules. And the unit for power is joules per second, which we usually write as watts. So if you look like at a light bulb and it says it's a 60-watt light bulb, that means it's using 60 joules of energy every second. Do you have a question, Ethan?
I don't think so.
Okay.
What were the units for work?
Work and energy are both joules.
Is it joule and Newton meter?
Yep, we're gonna get to that here in a little bit. And we're not gonna cover power anymore today, other than its base definition. We'll come back to that in a future lesson and dig into it more, look at the equations we can use to find power values. But for today, I just want to give a brief definition. So in units or chapters 7 and 8 from your textbook, these are the three base terms, the three fundamental terms, and some simple definitions to help you sort of get a grasp. We'll look at a more textbook definition for work and energy here in a little bit. All right. So one of the principles that we already talked about last week when we were giving a little foreshadowing of kinetic energy is that energy is conserved. And often they'll phrase it in AP questions as no energy is lost to the internal energy of the system or something like that. And we'll define that a little bit further as we go today. But basically what we're saying is the energy of the system remains constant in total. It might be all kinetic and then later it's all potential. It might be partially kinetic and partially potential and later it's different percentages. But the amount in whole stays constant. So we can see energy being transferred from one object or system to another within the system, but it can't just be created from nothing or destroyed. So an object that's on the top shelf, we say, oh, it has potential energy, but it didn't just create that potential energy. Someone had to lift it up and put it on that shelf, right? So someone had to do work to make the energy stored in the object and give it the height. So it didn't get created from nothing. Somehow it was created from applying work. And we're going to also talk about the work energy theorem in a little bit today. And work and energy go hand in hand. When you do work, you're using energy, and energy is the ability to do work. It's a cyclical relationship, right? They go hand in hand. But work is more clearly visible and measurable, and energy is an ability or a capacity. So it's a bit harder to imagine or visualize. But it is conserved, which is very powerful in problem solving. Now, there's lots of different forms of energy. We can really divide it into three categories broadly. One category would be kinetic energy, and usually we use the variable K. For College Board, they use the variable K, and it is a capital K. So you have to be careful because lowercase k is a spring constant, but capital K is kinetic energy. And they have rotational kinetic energy on here, 1/2 I omega squared. They've got translational kinetic energy on here, 1/2 mv squared. So those are both on the list. Nothing you have to memorize. Then there's also potential energy. Potential energy, we usually use the variable U. And it is energy that's associated with the system's configuration or structure or position. Configuration is a loose term to describe its either position or arrangement within the system. And if you look on here, you'll see capital U in a couple places. Down here at the bottom, there's a U sub S, which is the potential of a spring to store energy. And it's 1/2 little k x squared, little k for spring constant. And then up here, you've got U sub G, gravitational, mg delta y. We talked about last time, mgh delta y would just be the vertical displacement, the height. So there's our gravitational potential. And then down here, we've got U capital G, and it's related to the universal law of gravitation. Now that one is seldom used, but it is on the formula if you ever would need that. But it's the potential energy stored within a gravitational force field. It's a little bit different, and like I said, it's very seldom used, but the spring potential energy U sub S and gravitational potential U sub small g, those two are very commonly used. We'll be using them a lot in the next few days, next few class periods. Now, the third kind of branch that we can think about is often referred to as internal energy. It's the energy stored within a system because of the random motion of the system's particles. That energy can be lost to the environment. So some books take the approach, like your textbook, that we call it internal energy. That is the energy that's in the system that sometimes does get lost to the environment. Other books focus on the fact that it gets lost to the environment and call it dissipated or thermal energy. And we'll mention both. We'll kind of go back and forth and talk about them. But when energy is quote unquote lost to the surroundings, it doesn't mean it was destroyed. It means it was converted to something else, but it's no longer in the system. So like a ball hits the ground and there's a sound. Well, sound waves are a form of energy transmitting through the air. So that means that energy was lost from the system of the ball and the earth and now is in the air. And the air isn't what's creating the gravitational pull, it's the mass of the structure of the earth, right? So now that energy was transferred from being gravitational potential or kinetic into sound and lost to the surroundings. So we'll keep breaking that down further as we go. But it's often referred to internal energy, which is confusing because in other books they'll talk about it as lost to the surroundings, which sounds external. But it has to be internal in order to be lost. So it just depends on your perspective. Are you focused on the fact that it's internal to the system initially, or are you focused on the fact that it gets lost to the surroundings later? But it's the same energy either way. It's just your perspective of where you're referring to it, or how you're referring to it. So just some quick energy transformations. If we take the radiant energy from the sun, that solar energy, and convert it to electrical energy using some sort of solar panel, then we can use that electrical energy to turn a motor, which could lift an object and give that object gravitational potential energy. But then if we disconnect that from the motor, it's going to fall, and that gravitational energy turns back to kinetic energy, and it's just a system or a cycle of converting one form of storing the energy to another form, and recognizing it's never created or destroyed. It came from somewhere. It didn't just appear. And down at the bottom, you can see it says some energy might be changed into a form that isn't very useful to us. So when it gets changed into sound waves vibrating through the air, unless we want that, unless we're trying to create sound we want people to hear, that's not super useful. And then, but the fact is, it still doesn't mean that it was destroyed. It was just transferred to a form that's maybe not what we need. All right, so let's look at another transformation. If we have a ball that is moving along a table, for instance, and collides with the spring, and that spring compresses, the spring is going to compress, but has restoring force. It's going to restore that energy back to the ball. And if we think about the energy transformations here, the ball has kinetic energy because it's in motion. And as it collides with the spring, it's going to compress the spring by applying a force. Well, we said work is applying a force over a distance, and it applied a force over a distance to compress the spring. And we said energy is the ability to do work. So there must be a transformation of energy here because work was done. And that kinetic energy of the ball gets transferred into elastic potential energy in the spring. But then the spring is going to then restore its original shape and transfer that stored energy back to kinetic, and that's why the ball flies back the other direction. So if we kind of summarize it here, can I get someone here in the room to read this top part of the slide, the two bigger font portions? Okay, thanks, Johnny.
The kinetic energy of the ball is transformed into potential energy of the spring. As the spring's change in configuration is reversible, the spring can store energy in the spring's change in configuration. The spring now has potential energy.
And then as we saw in the original animation, that potential energy can reverse and become back stored back into the movement of the ball. Can I get someone in the Zoom to read the parenthetical part in the smaller font down there at the bottom for us?
Yeah, I can do it. Remember, an object can have potential energy. A system can have potential energy. A spring is a system and can change configuration.
All right, so again, sometimes we think, well, wait a minute, that object has potential energy because it can fall off that shelf. Well, it only has it because the Earth's gravitational pull. So the system is actually the object of the Earth. So we have to think about what actually is in the system. And a single object can't have any sort of energy stored unless it's a part of a system. So here we got the ball spring system, and that ball's kinetic energy can store as potential energy in the spring. All right, so here's your book definitions. Could I get somebody else in the Zoom to read the first one at the top for us?
Yeah. Energy is a quantity that is used to measure the state of an object or system or its capacity to cause motion.
So you can see some similarities into what we looked at on the previous slide with some bullet point definitions. They're a little shorter. This is a bit wordier, maybe a little bit harder to digest, but if you really break it down, you can see that it's trying to say the same thing in a different way for what we had on the previous slides. I'm going to get someone in the room to read the second definition for work.
Sure. Work is the transfer of energy from one object or system to another through a mechanical process that happens when a force is exerted on an object or system along its direction of motion as the object or system moves.
You know, it's a long definition if you have to take a breath in the middle, right? So, so again, we have a much wordier definition, but you can see a lot of the similarities here. We're applying a force. There has to be a direction of motion. There has to be a displacement. There's some sort of mechanical process in a system involved. So there's a bit more detail here. Definitely a wordier, harder to digest definition, but some good detail here. So if you're in the Zoom, you may want to, copy this down or find it in your book as you review. Hopefully you'll be reading through chapters 7, 8, 9 to review and practice and prepare. Or if you're in your class, you could write it down, you can take a picture, but these two book definitions are a little bit more formal. There's a little bit more detail, and especially the one for work, the second one. The emphasis in both of them that there has to be a system. And so a couple things there that I think are valuable, even though maybe they're not ones I would expect you to memorize word for word. They're pretty wordy, but I do want you to be able to break them down and understand what they're saying. So far, any questions about energy or work? We spent quite a bit of time defining them both. All right, let's get to some little bit more practical application of the two. Let's start with work. As we said on one of the first slides, and then just reemphasize on the last slide, work is done when a force acts parallel to the displacement. So if we've got our weightlifter guy here, he's applying a force upward and the weights are being displaced upward. So because they're in the parallel direction, he is doing work on the barbell and the weights. Now, in the gentleman on the right mowing his grass, he is applying actually an angled force down and to the left, or my left. And yet there is a component that's parallel, right? The X component would be parallel. So is all the force he's pushing with doing work? No, only the part that's parallel, only the X component. So a lawnmower design isn't necessarily the most efficient for maximizing the amount of work you're getting done for the energy you're putting into the system, because you're applying a large amount of force, but only a portion of it goes in. So you can actually get more work done by having a shorter angle, a smaller angle. So a shorter person gets a little bit more leverage if they can adjust the angle down and they're actually making it more parallel, than their X component is a larger value. Or if you get down on your hands and knees and push it, but then that's a whole other energy conversation. You're having to do a lot more work in that regard. But in terms of just literal force applications, the more parallel you can make it, the larger the amount of X component that's actually doing work, and only the X component does work. Doesn't mean the other part of the force doesn't exist, just means it's not doing work. And that's where we have to start separating our brains, thinking of work. If I hold my body in a plank, I might say I'm getting a good workout, trying to build some muscle, trying to build some strength. But am I doing work in a physics sense if I'm holding my body still in a plank?
No.
I'm not moving through any displacement, right? So if there's no displacement, there's no physics work being done. Is it a workout? Yeah, I'm going to sweat and get tired the longer I hold it, but it's not work in the definition of physics. And so it's a different kind of process that we're talking about there. for work, we have to make sure it's a force applied through a distance. So in this person picture pushing the box, they're pushing with a force parallel to the ground. The box is moving parallel to the ground. And so all of that force that's parallel is doing work, but only the force is parallel. So if he's pushing at an angle, he's losing some effectiveness. So if I want to move something that's really heavy, I get down lower and slide it by moving a couch. If I stand at the top, I'm actually pushing down into the ground and I'm losing some of my effectiveness, right? If I get down low, I'm giving a greater X component. See, we do those things naturally because we've kind of figured out through our living that it's important, but now we're understanding hopefully the physics behind it.
Yeah, I never
So-
thought of it like that.
4 scenarios, work or not work. So a man holds out a heavy concrete block at arm's length for 10 minutes. He's just standing there.
Just wising.
Okay. Is he performing work in a physics sense?
No.
No, there's no displacement. And he's going to get super tired. And if he can actually hold it there for 10 minutes, he's super strong and has a lot of endurance. But he's not doing any work in the physics sense because there's no displacement. A student pushing the car down the street.
Yes.
Yeah, they're pushing it parallel to the ground, at least some component, because the car is moving and the car is moving in the same direction that they're pushing, and there's some parallel relationship there. So there is work being done. A woman holds a box overhead while walking at constant velocity.
Not working
Yeah.
sense of the box, but she's walking, right? So it is work.
So is she doing any work on the box?
No.
No, not doing any work on the box. Now, is she doing any work on her body?
Yes.
Yeah, not on the box. So we have to maybe define it further, but to get up to constant velocity, she would have to do work because she would have to take the box from rest horizontally to moving. But once the box is moving at a constant velocity, does she need to keep applying a force to keep it moving at a constant velocity?
I mean, she has to like keep her hands up.
Yeah, assuming we can ignore air resistance, we can say, well, that box should just keep going, right? We know it won't
The box just
because
floats.
of there are errors and stuff. But if we really try to think about it on a base level, that her perpendicular force upward, even though she's moving this way, she's lifting this way, those two force or the force and the displacement are
Opposite. Or like,
Perpendicular.
perpendicular, yeah. So if they're perpendicular, there can be no component that's parallel, right? This force is straight up, that movement's straight that way. So that is not work if we break it down. Now, if we want to start getting into the nitty gritty, well, is she doing work on her body? Was she doing work on the box? Is there air resistance? We could take it further. I mainly just want to make sure you're getting the idea that we need a parallel component. A child pushing the cart along the sidewalk, obviously, like pushing the car, that's going to be work. All right. Let's think about definitions now in terms of equations. So here we have a force being exerted on a box, pushing it up a slope, and the box has a displacement that's also up the slope. Well, we defined work as force times displacement, right? Force and displacement. We're applying a force over a displacement. So the simplest form of the equation for work is just F times D. If I'm applying a force that's parallel to the displacement and I take the amount of force in newtons times the displacement in meters, I am finding the amount of work done in Newton meters. Now it's not causing rotation, so we would not define this as torque, even though torque also is measured in Newton meters. So this is one area where we have common units, but they're derived from a different meaning, and so we have to be careful about the context of the question. There's no torque here, even though it's also Newton meters, because there's no rotation. All right, and then in the second part, it says if a force is exerted perpendicularly. So if we drew the free body diagram for this orange box, there is a normal force perpendicular to the ramp. But because that's also perpendicular to the displacement, that normal force is doing no work. It doesn't mean the normal force doesn't exist, it just means it's not doing any work on the box because it's perpendicular to the displacement of the box. So if we think about a few more things, so let's add some more things that they haven't. Let's take it a little beyond the book here. They've shown two forces, right? On this scenario. What's another force that would exist if we were drawing a free body diagram for that block? Gravity or weight force. Which way would the gravity or weight force be directed?
Straight down.
Straight down. if it's straight down and we angle our axes so that the normal force and the force up the slope are both on the axes, what's going to be true about the weight going straight down?
It's gonna be parallel to the gravitational force.
It's gonna have a little bit of lateral force.
If our axes are angled, it has to be an angled force, not on either axis. So it's going to have an X component and a Y component. The Y component would be parallel to the normal force. So would the Y component of the weight be doing any work?
No.
No, it's perpendicular to the slope of the ramp. The X component, would the X component be doing any work? Negative work. Yeah, it's work in the opposite direction.
Yeah.
You're having, if you want to apply force up the ramp, you're applying force up that way. That's positive work because you're pushing it in the same direction it's moving. Gravity's trying to fight you, right? So it's doing negative work against you. What else might be doing negative work here?
Friction.
Friction. So unless this is one of those magical frictionless ramps, which would be hard to walk up, that means there's probably going to be friction doing work, and friction would be parallel to the surface, right? If friction's parallel to the surface, then it's also going to be doing work. All right, so we have to think about potentially a lot of different forces, which ones have components, which ones are parallel, and only the ones that are parallel should be factored in. All right, so now we're going to get to a little bit more of the equation. Well, what if instead of it moving up a ramp where we can just change the axes, what if it's actually moving on a flat surface, but our force is at an angle? Well, in that case, we have to think about the parallel component. We have to think about the X component. So to convert from my actual angled force to just the X component, I need to use cosine. So hopefully this is looking kind of familiar. Work is FD cosine theta. What's torque?
FR sine theta.
Yeah, FR sine theta or FD sine theta. We could switch the R's and the D's. They have a similar meaning in the sense that they're both distances, right? It's a little different because the R is a radial distance from the point of rotation, and D is actually the displacement. So functionally, these formulas are different. And in torque, we only want to know the perpendicular component. That's what's going to create the torque. The horizontal component doesn't create torque. It either just pushes or pulls on the pivot point. For work, we need the horizontal component because the perpendicular component doesn't do any work. Okay, so there's some connections. They end up having the same units, but they are defined differently and they mean something different. So you have to be really careful that we don't just say, oh, if that's how much work is done, that's how much torque there was, because they're both Newton meters. But torque is only about rotation and work is not. Okay, now it doesn't mean you can't do work and cause something to rotate, but you can't just say they're interchangeable just because they have the same units, because they're functionally defined in different ways. All right, so let's break down a little bit more. Where does that whole cosine part come from? Probably we've done enough with trig so far this year that you can make this out in your own brain, but real quickly, if we think about that force in red at an angle, there's both an X component, which we would use cosine to find, and a Y component, which we would use sine to find. And the cosine horizontal component would be doing work because it's parallel to the displacement. So if we figure out its value, we would take FD cosine theta to find its value. Now, if we think about this sine value, that is perpendicular. So it is doing no work. So no work by the vertical component because it's perpendicular to the displacement. In total, we could say, well, the total work of the system would be the work done by the X component and the work done by the Y component, but we just proved the Y component 0. And you can think about it with the math behind it as well. The cosine of 90 is what? 1. Sine of 90 is 1. Cosine of 90 is 0. So perpendicular force doesn't create any percentage, right? 0%. All right. So there's a little bit of the math behind why we use cosine, how it gives us the horizontal component. All right, and then Evan talked about positive versus negative work. Here's just a quick summary. In the first examples here, we've got a force to the left and a displacement to the left. We can take FD cosine theta. We've got cosine of 0, which is
0. Oh,
90 degrees.
wait.
cosine of 90 is
Wait,
0.
yeah.
Cosine of 0 is
90?
0.
Wait,
Wait,
0.
Cosine. of
1.
0.
1.
Yes.
all right. And then if we have an angled force, we've got 30-degree angle. And so we do cosine, FD cosine 30, so it's gonna be FD times 0.866 if we take cosine 30. But because they're in the same direction, we would call that positive work. Now, negative work would be where there's a force going in the opposite direction of the displacement, like friction, like gravity pulling something down a slope while we're trying to push it up the slope, right? Those kind of forces are still parallel potentially, or at least a component would be parallel, but we give it a negative value because it is opposite in direction of the displacement. So there's still work being done, but we call it negative work because of its direction.
Be kind of like a vacuum.
Wait, so how did it?
Wouldn't
how
have to
does
be a
it
vacuum,
move?
but
Oh, wait, never mind.
so like if I throw a ball to you, Evan, you have to catch it. So it's moving this way, its displacement's this way, but your force is that way to stop it. So you're doing negative work on the ball. In terms of the negative tells us the direction of the displacement compared to the force we apply. All right. And then if we have perpendicular, then we've got the cosine of 90, which is 0. So we get no force, or sorry, not no force, but no work. All right. The units for work are Newton meters, which is the same as the units for torque. And here we can see why it is FD cosine theta, forces in newtons, displacements in meters, so we get a Newton meter. But for work and energy, rather than using Newton meters and potentially confusing it with a different concept of torque, we typically write it as joules, even though technically it is a Newton meter. And joules is capitalized and it's spelled the way you see it on the screen here, Joule after a person's name. So it's not like a jewel ring, like a diamond ring or ruby or something. It's a jewel after a person. So that's why I use a capital J. And that's why it's spelled this way, not as like a rare jewel. All right. So we usually use joules for work and energy and keep it as Newton meters for torque. So we can clearly see where that value was determined. Was it by the rotational torque or was it just by the work or energy that was done? Work energy theorem, then we'll wrap it up with these couple of slides here. Another way to define work, we said, was how much energy transformation occurs. That was one of the first definitions we came up with, and it was also part of the fuller textbook definition. So another way to think about it is the work done on an object is equal to the change in its kinetic energy. So work equals delta KE. Work is in joules. KE is in joules. If we think about the equations, let me jot some stuff down here. So work is F d cosine theta. And kinetic energy is 1/2 mv squared. So here we get newtons times meters. Here we get kilograms times meters squared over seconds squared, which is newtons times meters. All right, two different equations, but functionally the same units, and also by definition, we know that they go hand in hand. This is extremely powerful. If the question says how much work was done, but they only tell you the change in velocity, well, you can use kinetic energy and find out how much work was done, even though you didn't use the equation for work. If they said, well, how much kinetic energy was there lost or gained? And they gave you F and D. Well, then now you know the force and the distance. So you take that and figure out the work done. That is the amount of change in kinetic energy. So you can find kinetic energy by using the definition of work. You can find the work by using the definition of kinetic energy. And this work energy theorem is extremely helpful for problem solving. All right. So real quick, wrap up with this and then an example. So how is energy divided in a system? We've talked about this before. This is kind of a quick summary. we usually think about it as two buckets of energy. One is the kinetic energy of motion, the other is potential energy. But then potential energy could be for a few different ways. The three most common: gravitational, elastic, and chemical potential energy. We will very, very seldom think anything about chemical potential energy. If you've taken chemistry, then you probably learned about calorimetry, and there is a way we can find the amount of calories or joules of energy stored in the bonds of chemicals. But we're going to leave that for chemistry primarily and focus on the elastic and gravitational potential energies. Now, there is that whole other internal energy we talked about before as well, which we will sometimes say, well, that's the energy internal to the system based on the vibrations of the particles. But that's also the same energy that can be dissipated or lost to the environment. So again, depending on your perspective, am I focused on what was there to begin with, or am I focused on where that energy is to end with? We might call it something different, but we're referring to the same thing. So in quick summary, this one's all the different types with the various variables you're going to see. So kinetic energy, College Board uses K, but you also will see E sub K or KE quite frequently, but it is the energy of motion. Potential energy, College Board uses UG if it's gravitational, but you sometimes will see EG. Either way, it's the energy stored due to the separation of two objects that have mass. Because if you remember how we calculate gravitational force, it's the constant times mass 1, mass 2 over r squared. So it's their separation, their radial distance, and their masses. Elastic potential energy. College Board uses U sub S, but you might see EEL or UEL for elastic. S is for spring and EL is for elastic. So again, quite a few different variables you might see from book to book, worksheet to worksheet, meaning the same thing. But it is the energy stored in a temporary deformation of a spring or a bungee cord or a rubber band or a rubber ball or something like that. And then the last one, those three are italicized, or not italicized, but they have a little asterisk beside them because those are the three that we mostly work with. But occasionally they say, well, you shouldn't ignore friction. We do want you to consider friction, or we do want you to consider that internal energy that could get lost to the environment. And so in that case, you see even more variety. Sometimes it's ED for the dissipated energy. Sometimes it's ETH for the thermal dissipated energy. Sometimes they use U instead of E. It is that energy stored in the microscopic vibrations and motions of molecules. And it's initially there in the system. It could potentially get lost to the environment. So we typically see it lost as sound or light or heat, something like that. Sometimes they'll say ignore that. Sometimes they won't want you to ignore it. So you just have to think clearly about what they're saying in the wording. So this is a nice little summary of all the variety of variables you'll see. Unfortunately, there is a fair bit of variety. All right, let's do an example to think it through. So we have a ball being held above the ground, and then it's dropped so that it falls straight down. We're going to restrict our analysis here to just the ball being in the air. So from the point that it's dropped until the instant it makes contact with the ground, but hasn't had a chance to compress or bounce or anything like that. It's like right at the instant it touches the ground. So what kind of energy does it have at the top?
Potential.
Gravitational potential.
Yeah, gravitational potential. Based on its height, it has gravitational potential. It's mgh, right? How about at the very bottom, right as it's touching the ground? Or as it's starting to touch.
Zero potential energy.
Yeah, its height is 0 now, so no potential. So what does it have?
Kinetic.
Kinetic. So here it's UG, here it's K, and so we're talking about 1/2 mv squared. It's got velocity with its mass. What about in the middle? Both. Does it still have height in the middle?
Yeah.
Yeah, so it still has mgh, but it's less now. Is it going maximum velocity at that point?
No.
Probably not. I suppose there's a way it maybe would reach terminal velocity, but most scenarios it wouldn't. Right. So it's still
Would it be by
accelerating.
1/4? of like the 1/4 MV squared?
It says 1/2 MV squared.
No,
Or-
in the middle.
Uh-huh. Oh, no, well,
'Cause
we don't.
would it be split?
Because acceleration is nonlinear, you can't just change the fraction. You actually would have to use kinematics to figure out what the V is at that point. Great question. I didn't understand it at first, but yeah. So even if we said that, I mean, it's hard to tell whether that's halfway or not. But even if they did say specifically it was halfway, you can't just say it's 1/4 of the kinetic energy because it won't be, the velocity isn't changing in a linear manner. The velocity is changing, or the velocity changes in a linear manner, but the velocity value is not going to be, or the energy is not going to be changing in a linear manner. So what I really want is just for you to recognize that there's going to be some kinetic energy because it is moving, but not at its maximum speed yet. And then there's going to be some potential energy because it still has height. Fraction wise, we would need to know a little bit more information than what they're giving us here. But I'm just wanting you to start to imagine this as pie charts. Like at the beginning, it's 100% gravitational. At the end, it's 100% kinetic. And in the middle, it's going to be some split. But we do have to actually use kinematics to figure out what the velocity would be at that point. All right, any questions? All right, well, that's where we're going to stop for today. Got about 7 or 8 minutes here, I think. For those of you that are in the Zoom, if you have questions for me about positive physics or about anything we've covered today, you can stick around. If not, though, you can be dismissed, and we'll see you on Wednesday when we're going to do some FRQ review.
Thank you.
Thank you.
For you guys here, like I said, we will be doing FRQ review that day. It'll be actually the first true FRQ that's not specific to a particular unit. It's actually from College Board. It was a previous test question. So we're ready to graduate to the next level. That'll be Wednesday. And then Thursday, we'll come back to this more energy and work. For you guys in the class, you can start packing things up. Once you're packed up, we can start cleaning up the tables and getting you guys ready to go.